Hello everybody, this is Dr. Christopher White and today we are on to lecture 16. So once again it's going to be in two parts. So we're going to be dealing with the Mesozoic Earth history, so what's going on with North America and the rest of the world during the Mesozoic. Alright, let's get going. So during the Paleozoic we had four major marine transgressions. So if you remember, a transgression, it's when the ocean comes over the land. And during these four transgressions, we produce four empiric seas. These are shallow bodies of water. And these transgressions are termed the Sok, the Tippecanoe, the Kaskaskia, and the Absaroka. And each of them produced an empiric sea that either partially or completely covered the United States and the vast majority of what is now modern North America. We also had orogenies on the east coast. So we had the Taconic orogeny, the Acadian orogeny, the Caledonian orogeny, the Achetan orogeny, and the Elegahenian orogeny. Well, that's on the east coast. And we had a minor orogeny on the west coast, which was called the Antler orogeny. We also see that life exploded and diversified, but there were several minor and major extinction events during the Paleozoic as well. So during the Paleozoic we had the Ordovician Silurian, Devonian Carboniferous, and Permian Triassic mass extinctions. We also have plants invading the continents from the late Ordovician onwards. We have amphibians showing up in the middle to late Devonian, and we have reptiles appearing in the late Carboniferous. So it was all go pretty much for the world during the Paleozoic, especially towards the end. So the transition from the Permian into the Triassic is marked by two things. The first thing is that we see a lot of organisms disappearing that were present in the Permian. So of course, if you remember, the Permian Triassic mass extinction occurs and it kills off a lot of organisms. And so to start with, when we look at the rock record, we see the loss of a significant proportion of these organisms. So that tells us that we've crossed the boundary from the Permian into the Triassic. The other thing that begins to show us that we've moved from the Permian into the Triassic is we begin to see the first indications of the breakup of Pangaea. So if you remember, Pangaea formed when Gondwana made contact with Laurasia during the late Carboniferous to early Permian. Excuse me. And by the end of the Permian into the Triassic, that supercontinent is now falling to pieces. So by looking at the magnetic signatures from oceanic crust and also dating the oceanic crust, we can see the history of Pangaea's demise, because obviously when two pieces of continent move away from each other, well, the space in between them gets filled by an ocean basin. And so we can actually see the start of, the date on which that ocean basin starts forming. We can find the oldest oceanic crust, we can date it, and we can say, right, this is when the oceanic crust started forming, so we know when these basins began to be produced. So we know that rifting of Pangaea began along the contact between Laurasia, so that's Laurentia plus Baltica, and Gondwana. So Gondwana is South America, Africa, India, Antarctica, and Australia. And we know it began in the mid-Triassic. However, we didn't actually see an ocean basin forming between those two supercontinents until the early Jurassic. So it took a while for an ocean basin to actually form. So the rift that would eventually go to form the Atlantic Ocean began in the northeast of the suture zone between Gondwana and Laurasia. Began in the northeast of the suture zone between Gondwana and Laurasia, and it progressed in a southwesterly direction. So we see that Laurasia and Gondwana have fully detached themselves from each other by the early to middle Jurassic. So this is our situation. So obviously towards the end of the Carboniferous to early Permian, we had the formation of Pangaea. So we had Gondwana come slamming into Laurasia, and that forms essentially a range of mountains that goes up from what is now southern Europe down the eastern seaboard of the United States and into what is now the Gulf Coast region. So that separates Laurasia from Gondwana. And at the same time over here, we had Siberia crashing into Baltica to produce the Ural Mountains here. And obviously that produces the supercontinent Pangaea. So what we're going to see is that rifting begins to occur along this suture zone here between Gondwana and Laurasia. And the rift itself starts up here in the northeastern corner, and it progresses in this direction towards the southwest. So, okay. So, in terms of the body of water that's surrounding Pangaea, okay, it was initially referred to, should I say earlier, as the Panthalassic Ocean. However, by the time we make it into the Mesozoic, it's now referred to as the Pacific. And we also have a very important body of water over here. This is called the Tethys Ocean. So the Tethys Ocean is very important because it is situated over the equator. It's a relatively restricted body of water, and so what we're going to end up with here is a nice warm body of water, a little bit like the modern Indian Ocean. And so this is going to have very interesting repercussions for water circulation later on in the Mesozoic. So this is the point, by the way, at which we no longer have Laurentia. We're no longer talking about Laurentia. We now discuss this piece of crust and we refer to it as North America. So North America essentially consists of Greenland's going to be about here, Canada's going to be about here, the United States is going to be about here, and pieces of northern Mexico are going to be somewhere around here. So okay, so we now have what we would classify as North America. So alright, so this is our situation in the early Triassic. So as we can quite clearly see, we have Laurasia here, Gondwana down here, and we have the suture zone here. We have the Hercynian Mountains in southern Europe used to be there. They've been completely eroded away. They're gone. The Achetan Mountains over here in the Gulf states, so here's Texas down here. They're pretty much gone as well. And we have the remains of the Appalachian mobile belt right here. You can just see it in this area here. We have a bit of the Appalachians left, but they also have been significantly eroded down. So this is the situation in the early Triassic. We also have the formation of a restricted body of water down here in the southwest portion of the suture zone. That's nothing to do with rifting. That's just some water that's gotten trapped in this area and is slowly evaporating away. So as we move into the late Triassic, we begin to see rifting develop along this suture zone. And we can see it developing because we begin to form lots and lots of big, long, normal faults, all running parallel to each other in an approximately northeast, southwest direction. And so this is telling us that the crust is beginning to undergo extension. It's beginning to be stretched. So initially, when you take a piece of rock and you begin to stretch it, for a short period of time, that rock will behave like a liquid. It will behave a bit like silly putty. It will begin, you can stretch it, and as you stretch it, it begins to become thinner. But you can't do that for very, very long with rock. So once you reach a certain point, the rock can't really stretch any further, and it begins to break. So instead of flowing like a liquid, it starts to break and fail like a solid. So when it begins to break and fail, that means essentially you begin to form blocks of rock, and as you pull those blocks of rock will drop down relative to one another. And as those blocks of rock drop down, well, they're going to form a topographic low, which we refer to as a rift valley. And one of the indicators that we have a rift valley is it will be a linear body, so you can see it here. This is our linear rift valley here. And we can see it has lots and lots of long normal faults that are all orientated parallel to each other. They are also orientated parallel with the elongation direction of the rift valley. And so that's showing us we have all these blocks of rock all dropping down relative to each other because this area of crust right here is being stretched. And it's being stretched because Laurasia is trying to go this way and Gondwana is trying to go this way. And so this area of rock in between is undergoing extension. Okay, so by the time we're into the Jurassic, what's going on? Well, the rift zone here between Gondwana and between North America has begun to become quite extensive, and we have the rift zone filling with water. So we have the start of what will become the modern North Atlantic. Okay, we can also see still in the Jurassic, we still have the Tethys Ocean here. Gondwana is still in one piece. Africa, South America, Australia, India, and Antarctica, they're all still together. North America is still in one piece. We still have Greenland, Canada, North America, a little bit of Mexico down here. And although it doesn't look like it because we have this line of water here, North America is still very, very firmly attached to Europe. They're still one landmass, which we're still referring to as Laurasia or Eurasia, depending on what you want to call it. Okay. So as we move into the Jurassic, we begin to see this rift valley starts to fill with water. Now this is still a restricted basin down here. Okay, the water itself is coming from the northeast and is going to start filling the basin from towards the southwest. So by the time we make it into the early Jurassic, we can see we have this deep line coming here. Okay, this is the formation of the ocean crust proper. Okay, so all of this rifting here has just been continental crust. It's at this point we start seeing the formation, well, the melting of the mantle underneath the rift. That melting mantle produces basaltic magma, mafic magma, that rises through the crust, pushes the crust apart, and creates oceanic crust. So at this point, we actually have the start of the formation of the North Atlantic taking place. Okay. So we also have the early stages of some rifting up here between Greenland and Scandinavia. Now, this isn't actually going to develop very much, but it is the very, very early stages of the rifting that will eventually lead to the separation of North America and Eurasia. Okay, so as we're going through the Jurassic anyway, this rift valley is becoming more and more pronounced. By the time we're into the middle Jurassic, you can see we have a solid line of dark blue here going all the way from the Atlantic all the way into now what is the modern day Gulf region. And so this is all new oceanic crust forming, so we now have a proper oceanic basin forming. So at this point, we have a rift that's running down the middle, creating new oceanic crust that's going to push North America this way up towards the northwest, and it's going to push Gondwana this way down towards the southeast. And as we keep going into the late Jurassic, we can see that the formation of the oceanic crust is continued to push North America to the northwest, Gondwana to the southeast, and the ocean basin steadily getting larger. We can also see that if you look here, here's Spain, or modern-day Spain, and you can see there's no rift here yet. But by the time we're into the late Jurassic, you can see a rift has started to develop here between, essentially along what is the west coast of Spain and Portugal. And it's coming up here. Here's the United Kingdom and Ireland, right there. And you can see this rift is starting to develop up here between the United Kingdom and Ireland and Greenland right here. Okay. Now, once again, this rift still isn't particularly well developed, so make it clear, North America and Europe are still attached to each other at this point. They're still one landmass. Okay, so by the time we make it into the Cretaceous, what's going on now? Well, the Cretaceous is marked by a period of very, very high sea levels. So the global sea level is about 250 meters higher than present day. And so this leads to very, very widespread global empiric sea. So we have a global marine transgression going on. So you can see Europe is nearly completely underwater. Large portions of coastal Africa are underwater. Northern South America especially is underwater. We have this what's called the Cretaceous Interior Seaway that bisects North America all the way from the Arctic Ocean up here down to the Gulf of Mexico down here. And we can quite clearly see that portions of Asia are also underwater. Now we can also see by this point South America, Africa, India, Australia and Antarctica have all separated from one another and they're all going off doing their own thing. Now, although this diagram shows that North America and Europe look pretty much detached from each other, they are still attached to each other until literally the last minute of the Cretaceous. Okay, so throughout the Cretaceous, North America, Europe, Asia, they're still moving together as one landmass. Okay, so by the Cretaceous, what's going on? So in the early Cretaceous, the North Atlantic and Gulf region is opening up nicely. We have lots of new oceanic crust forming, once again pushing North America off to the northwest, pushing Gondwana down here towards the southeast. And we can see that this rift that's starting here has kind of stalled out a little bit. It's still there, but it's not really growing very fast. You can see by the time we're into the later portion of the early Cretaceous, it's still there, not really developed very much. North America is still attached to Europe at this point. The North Atlantic and Gulf is still getting a little bit larger. It's steadily growing. By the time we're into the late Cretaceous, you can see the North Atlantic's getting larger, and you can see this rift has really started to develop now. Okay, we can see it's actually begun to split into two. One limb is coming up here, so it's going to come up between the United Kingdom and Greenland, and it's going to work its way up here between Greenland and Scandinavia. And another limb is going to come up here, and that's going to separate Greenland from North America. By the time we're into the very late Cretaceous, we can see these rifts have developed very nicely. We can see that the United Kingdom is now well separated from Greenland by oceanic crust. We can see Greenland is beginning to separate from North America, but you can also see that they are still attached to each other, just holding on. So in terms of the separation between North America and Europe, as I said, it really, the separation does not fully occur until right at the end of the Cretaceous. Another thing that you might have noticed is as we've been moving through, so if we look here, this is the Triassic, this region down here is going to develop into Mexico. You can see that over time, you can see that slowly but surely we have several island arcs appearing and attaching themselves into this region down here. So we have a subduction zone running down here, pulling oceanic crust this way, pulling material towards what is now modern-day Mexico. So you can see you have several of these island arcs moving across, and they're going to steadily collide with what is now modern-day Mexico and start to build up the mass of modern-day Mexico all the way through the Mesozoic. We can see Mexico steadily getting larger, and as we move into the late Cretaceous, we can see that modern-day Mexico is nearly fully formed at that point. So, in terms of Gondwana, it began its breakup during the early Triassic, through the Jurassic and into the Cretaceous. So remember, Gondwana is South America, Africa, India, Australia, and Antarctica. So, along with the rifting along North America's east coast, a large subduction zone formed along the northern margin of the Tethys Ocean. So here we go. So if we go back here, we have a subduction zone that's running all the way along here, and it continues all the way along here, along the southern margin, well, if I should say along here, essentially cutting through the center of Europe. Okay? So what this is going to do is as Gondwana starts getting pushed this way, away from North America as the North Atlantic opens up, we're going to get South America and Africa start to rift off from each other, and then the force, this subduction zone that's running up here, is going to start pulling material in this direction. So it's going to start pulling Africa up towards Europe. Now, eventually, Australia is going to separate from Antarctica, and that's going to start being pulled northwards by the same subduction zone. And India is going to do the same thing. India's around here, and India is also, when it separates, is also going to start being pulled northwards by the subduction zone running along here. So that subduction zone is quite important because it explains why Africa, India, and Australia all start to move the way they do. So the subduction zone began to place a small stress on Pangaea because it was encouraging Gondwana, or more accurately South America and Africa, to move in a northeasterly direction. So in the late Jurassic, a landmass consisting of Antarctica, Australia, and India rifted off Gondwana's eastern margin. So in the late Jurassic, you end up with two landmasses. Gondwana splits into two. One landmass is Africa and South America. The other landmass is Australia, India, and Antarctica, and they start separating. They start going their own way. And the rift that's pushing them in different directions will now go to form what is now the modern-day Indian Ocean. So we also need to remember there's still this northerly pull, though, towards Asia that's trying to take Africa, India, and Australia in an approximately northerly direction. So not long after this rift occurs, we then get the separation of India and Madagascar off this new landmass. So in the late Jurassic, we form this landmass of Antarctica, Australia, and India, and then in the early Cretaceous, India and Madagascar rift off that landmass and start going off to do their own thing. So in the early to middle Jurassic, we also begin to see the formation of a rift between Africa and South America, and that's going to develop into the South Atlantic. And we have a complete ocean basin by the middle Cretaceous. So by the middle Cretaceous, South America is completely separated from Africa. So South America starts moving in a westward direction. Africa starts moving in an easterly direction. And of course, Africa's also being pulled northwards by that subduction zone. Australia and Antarctica stick together all the way through the Mesozoic. During the early to middle Cretaceous, we begin to see Australia wanting to try and move in a northerly direction, and Antarctica's trying to move in a southerly direction towards the South Pole. And so we begin to see that extension of those two continents, essentially resulting in rifting and full separation by the late Cretaceous. In terms of North America, Europe and Asia, well obviously Europe and Asia stay stuck together, that hasn't changed. In terms of North America and Europe, the contact between suture zone between those two land masses, well that contact essentially stays complete until it's a bit difficult to work out exactly when the separation completely occurred, but essentially the suture zone between North America and Europe is intact until literally either the very, very last minute of the Cretaceous or maybe just into the Cenozoic. Okay, so it's been 20 minutes, so let's pause now, and then when you come back, we will have a look at these maps here, which is going to demonstrate how how Pangaea fell to pieces. All right, so pause the presentation, go and get a glass of water, have a walk around, relax for a few minutes, and then please come back. Okay, so this is the situation in the early Triassic. So here we have Pangaea. So we've got Asia over here, the Ural Mountains here. This is Europe. North America's here. We have South America here. In fact, you can just kind of make out the west coast of South America there. We have Africa here. So here's that kind of the northwestern Africa. It's going to come around like this, come around here. So this is going to be Saudi Arabia here. Egypt's going to be around here. Libya, North Africa is going to be around here, the southern coast of the Mediterranean. We have India about here. We have Australia over here, and we have Antarctica down here. Okay, so at the early Triassic, what starts happening? Well, to begin with, we have the Tethys Ocean here, and we start forming several subduction zones along the northern margin of the Tethys Ocean. And so this is going to start taking all of this oceanic crust here, and it's going to start pulling it in this direction. And it's going to start stretching all the pieces of crust it's going to start taking all the pieces of crust that it's attached to with it. So Africa, India, Australia, Antarctica, they're all going to start being pulled in this direction. Now at the same time, we have the rift opening up here between North America and what is now modern day South America and Africa, and that's going to start pushing this entire landmass towards the southeast. So we have two forces operating on Gondwana, one pushing southeast and one pulling northeast. At the same time, we obviously have this pushing force now due to the creation of the North Atlantic, and that's going to start pushing North America this way. And obviously, as Europe and Asia is still attached to it, they're going to go with it, and they're going to rotate a little bit as they go. So by the late Triassic, what's going on? Well, the rift here between North America and Gondwana is developing nicely, and it's slowly but surely beginning to fill up with water. Still not a complete oceanic basin yet. We still don't really have oceanic crust being made. Now you can see by this point, we'll just go this way a second, we can see there hasn't been too much movement from the early Triassic into the late Triassic, but you can see there is a little bit of movement there along the north coast here of Gondwana. But by the late Triassic, this rift is developing. It's still pushing North America this way, Gondwana this way, and these subduction zones over here are still operating, and they're still trying to pull Africa, India, and Australia in this direction. Now, the most important thing though is we also have another rift opening up here. Okay, and this rift is going to develop, and it's going to separate India, Australia, and Antarctica from South America and Africa. So as we move into the early Jurassic, we now have a fully formed rift between North America and Gondwana. So now we have the North Atlantic. Gulf Coast region is down here. We now have this rift beginning to further develop here between Africa, India. So it's going to slowly cut down here. It's going to separate off India, Australia, and Antarctica. And once again, though, we still have these subduction zones working up here, and they are still going to be pulling Africa, India, and Australia. They're going to try and make them move in an approximately northeasterly direction. By the late Jurassic, you can see, okay, now we have most of the continents beginning to separate away from each other. Okay, so the North Atlantic and Gulf Coast and Gulf region has opened up nicely. We now have the start of rifting between South America and Africa. You can begin to actually see South America and Africa properly now. we have a fully formed rift here that's now separated off India, Antarctica, and Australia. And we can see the rift between India, well, this is actually India plus Madagascar, is now slowly starting to rift off the side of Antarctica. Once again, we have the subduction zones here. These subduction zones are pulling Africa in a northerly direction. They're trying to pull India in a northerly direction, and they're trying to take Australia in a northerly direction. Now this rift here, though, is taking Antarctica and Australia in an approximately south-southeasterly direction. This rift here is going to start pushing South America this way and Africa this way. So what you can see is that Africa is essentially being pushed both this way and pulled this way. So it's going to start rotating towards its current position. So this corner here is going to start coming up. It's going to start hinging around here, and it's going to start sweeping up, and so until it's in its modern orientation. So by the early Cretaceous, this rift between Africa and South America is developing nicely. We have a nice ocean basin here between Africa and India, Antarctica, and Australia. So at this point, India is now fully separated, and it's going to start going on its journey towards Asia because of this subduction zone here, pulling the oceanic crust this way. Once again, the subduction zones along here is pulling Africa, trying to make Africa move in a northerly direction. Still attached to South America, so it's still not quite there yet. Antarctica is now trying to move straight towards the South Pole. And at this point, you can see the rift between Australia and Antarctica is beginning to form, because Australia is still wanting to move in a northerly direction along with India. And by the time we're into the late Cretaceous, we have full separation of South America and Africa and the formation of the South Atlantic. Now this means that Africa can now move this way and this way. You will have noticed as we go back to the previous slide, you'll notice that it's begun to rotate. So look at the southern tip here of Africa. You'll see it starts off over here, and by the late Cretaceous it's over here. So you can see the continent's beginning to rotate slightly, so it's rotating around here, and the southern point and this eastern side is coming up like this. That's because it's being pushed this way and pulled this way. We can see by the late Cretaceous, Madagascar is separated off India, and it's going to essentially it's going to move towards Africa, where it's going to essentially stick itself onto the side of Africa, and that's going to be it until the present day. India is now going to start moving towards Asia, and I want you to take notice of all of this continental shelf to the north of India, all of this continental crust here that's underwater. Okay, so this is about the size of modern India here. So all of this material here is going to get squished when it hits Asia, and that's what's going to form the Himalayas. By the late Cretaceous, you can see Australia is nearly completely separated from Antarctica. By the very end of the Cretaceous, it will be a separate landmass in its own right, and it will be moving towards the north. Antarctica is trying to move over the South Pole. It's nearly completely there. As we can see up here, by this point we can see we have these rifts developing nicely. So North America and Europe are nearly completely rifted off each other, and the rift is developing nicely between Greenland and North America. So you can see by the late Cretaceous we have essentially the modern continents around. We can see where they are, and we can see approximately where they're going. So okay. So now let's focus in on North America, and let's start thinking about the Mesozoic sequences. So let's start thinking about these shallow bodies of water that form on North America during the Mesozoic. So the transition from the Permian into the Triassic is marked by the Absaroka sequence. So the Absaroka sequence straddles the boundary between the Permian and the Triassic. So the Absaroka Empiric Sea was mostly limited to Laurentia's west coast and southern margin, give or take a little bit. Okay, so if you remember the Soak, the Tippecanoe, and the Kaskaskia, those marine transgressions resulted in the near complete coverage of North America by water. So if you remember, for both of those three sequences, the United States was completely underwater, and a significant portion of Canada was underwater. And so this meant the supply of detrital sediment, clastic sediment, was severely limited because there wasn't that much land above sea level which could be eroded. So that means that the water that was being, that means there wasn't much clastic sediment being dropped by rivers into those Epiric seas, into the Soak Epiric Sea, the Tippecanoe Epiric Sea, and the Kaskaskia Epiric Sea. And so this means that the water quality for those Epiric seas was extremely clear. It was shallow water. They were situated over the equator, so it was warm water, and so that meant huge quantities of carbonates were deposited during those free marine transgressions. Now, in contrast, the Absaroka transgression left large portions of North America above sea level. We also had the remains of the Inuitian orogeny up here, the Caledonian orogeny over here, the Appalachian mobile belt here, the Achetan mobile belt down here, and the Proto-Rockies down here. So essentially what we have is a situation where we have loads of high ground. High ground will naturally be eroded very, very quickly, producing huge quantities of sediment. Then we had a plain, essentially, which would have been covered by massive rivers that would have transported all of that eroded sediment from these upland areas and deposited it into the Absaroka Epiric Sea. And so this means the Absaroka Epiric Sea had huge quantities of clastic sediments going into it. So the water quality was nowhere near as good as the water quality that occurred during the Soak, the Tippecanoe, and the Kaskaskia. So that's why we don't see large-scale carbonate formation during the Absaroka Epiric, as part of the Absaroka sequence, because the water quality was nowhere near as good. We do see limited carbonate formation down in this southwesterly corner down here. This is the area where water quality was probably at its best. And so we see carbonates forming down here. However, the rest of this area here, that's going to be dominated by clastic sediments. So we're going to see lots of sandstones, lots of mudstones in this area here. A few carbonates forming down here. So here we go. So this is the Mesozoic here marked out in red. And we can see the Mesozoic itself. We're still in the last stages of the Absaroka sequence. We can see the Absaroka Epiric Sea has been retreating all the way through the Permian, and by the time we make it to the Permian-Triassic boundary, about half of North America is exposed. Going to the Triassic, there's going to be a small marine transgression, followed by a very large regression. And at this point, during the middle of the Jurassic, nearly all of North America is going to be exposed, so it's going to be actively eroded. And then as we move from the Middle Jurassic into the Cretaceous, we're going to steadily see a large-scale marine transgression, and we're going to see the formation of the Zuni sequence and the Zuni Epiric Sea. You'll also notice that during this period, we have no orogenies on the east coast, because that area is undergoing active extension. It's being stretched. So that means no convergent plate boundaries, so no mountain range formation. On the other hand, on the west coast during the Mesozoic, is nearly a non-stop subduction zone, and so that means there's lots of stuff hitting the west coast during the Mesozoic, and so that leads to the formation of the Nevadian, Sevier, and Laramide orogenies. So the large amounts of sediment coming from the eroding central and eastern portions of, I should say, North America, meant the Absaroka Sea was dominated by detrital sediments. And obviously, as I mentioned, that's a significant change in sedimentation compared to the three earlier marine sequences. So during those three previous sequences, I said water quality was relatively clear, warm and shallow, which meant large quantities of carbonate were formed. Okay, so the Absaroka Epiric Sea, that was pretty fast. The main sequence that occurs during the Mesozoic is the Zuni sequence. So the Zuni transgression began in the Middle Jurassic and extended all the way through to the early Paleogene. So it actually goes through to the very early Cenozoic. So like the Absaroka, it was not a complete transgression. So portions of central North America and the east coast of North America and the early Rockies remained above sea level throughout the Zuni sequence. So this means that once again we're going to have quite a bit of clastic sediment produced, so we're not going to see huge quantities of carbonate produced during the Zuni sequence. So what caused the Zuni sequence? Well, the Zuni sequence was likely the result of mantle plume activity forcing spreading ridges upwards. So it looks like during the Cretaceous especially, there was a lot of magma that got trapped underneath spreading ridges in the ocean basins. We think that most of this magma got trapped was from hotspots, so mantle plumes. So we think that during the Cretaceous there was a huge mantle plume activity. That meant you had these big balls of magma that came flying from the core mantle boundary all the way up through the mantle, and they got stuck at the base of the crust. And they tended to get stuck under spreading ridges. And obviously these balls of magma, they're very, very buoyant, they want to rise, and so they push up the crust above them, they make it dome up. And so essentially what that means is when you have all these mantle plumes stuck underneath the spreading ridges, well, they're going to push up the spreading ridges. And as they push up the spreading ridges, well, that means they're going to start displacing water. And as they begin to displace the water, well, that water has to go somewhere, and so it goes onto the land. And just to give you some idea, as I think I mentioned already, the sea level during the Cretaceous especially is predicted to have been about 250 meters higher than the present day sea level. So obviously this movement of water onto the land resulted in the formation of the Zuni Empiric Sea in North America. So the transgression that was part of the Zuni sequence actually took place in two phases. So if we just go back to this diagram here, you can see it makes it look like the Zuni is just one smooth event. Well, actually it's not. It actually takes place in two parts. The first portion of it produces what's referred to as the Sundance Sea, and that occurs between the Middle and the Late Jurassic. The second part of it forms what's referred to as the Cretaceous Interior Seaway, also sometimes referred to as the Western Interior Seaway. And that goes from the early Cretaceous to the very early Paleogene, so it makes it all the way into the Cenozoic. So the retreat of the Sundance Sea was driven by uplift along the west coast caused by the Nevadian orogeny. So what happens is we get this marine transgression right at the, we get this marine transgression that forms the start of the Zuni sequence, and that inundates the western side of modern-day North America. So the west side of modern-day North America is underwater. Then what happens is we get the Nevadian orogeny forming, and that starts to form the first stages of the Rocky Mountains. And so what we see is the west coast starts being pushed up as the Rocky Mountains start forming. Well, as that land starts to go up, it means the Empiric Sea on it obviously has to start draining away into the Pacific Ocean. And that's exactly what it does. Now, what then happens is during the Cretaceous, we get this sudden burst of mantle plume activity. Those mantle plumes get stuck under the spreading ridges, they push the spreading ridges higher, and that results in that 250 meter increase in global sea level. And so that very significant increase in sea level is sufficient to allow the water to go back onto North America, especially along the west coast. So, that increase in sea levels is enough to overcome the uplift of the west coast caused by the formation of the Rocky Mountains. Interestingly, only North America underwent a mid-transgression retreat. Everywhere else in the world didn't really undergo a retreat because nowhere else in the world was undergoing significant mountain building like in the area of the modern-day Rockies. So, for instance, Europe during the Mesozoic spent nearly the entire time underwater. So at the end of the Cretaceous and into the early Paleogene, we see the spreading ridges begin to subside as the mantle plume activity beneath them decreases. So that means, number one, is that as the ridges subside, that means they drop down. That creates empty space and the water flows back into the ocean basins from the land. And also, as we move from the Cretaceous and into the early Cenozoic, we begin to see the formation of ice sheets at the north and south poles, and that's going to start locking up water, and that's also going to cause global sea levels to begin to retreat. Or should I say decrease, leading to a retreat. Okay, so once again, here are our diagrams. So here's the early Jurassic, and we can see in the early Jurassic, the Rift Valley here along the eastern seaboard is developing nicely. We can see we have the early stages of the Rockies occurring down here. Okay, there's nothing really left of the Achetan mobile belt. That's pretty much eroded away. The Caledonian Mountains pretty much gone. Hercynian Mountains pretty much eroded away, and there's only a little bit left of the Appalachian Mountains. They're mostly eroded away as well. So essentially, we have a flat plain here. Now, as we move into the Middle Jurassic, global sea levels begin to rise, and we see water begins to move in from this northwesterly area here, and it starts to move down into the central and western United States. And so this is the Sundance Sea. Now, as we move into the late Jurassic, you will see that the Sundance Sea actually goes into retreat. So it's quite large there, and by the late Jurassic, it's actually retreating back into the Pacific. That's because the entire west coast is being pushed up as part of the early stages of the formation of the Rocky Mountains. So obviously, as this area gets pushed up, well, obviously the water on it starts to drain back out towards the ocean basin. And by the time we're into the early Cretaceous, you can see the Sundance Sea has fully retreated, and we have the Rocky Mountains developing nicely there. Now, as you move into the early Cretaceous, we then have this increase in mantle plume activity on the spreading ridges, and so these spreading ridges are getting pushed up, displacing seawater, and that seawater has to go somewhere, so it has to end up moving onto the land. So you'll notice areas like Florida, for instance, are well above sea level. Most of the southern states at this point are well above sea level, and obviously this area here is also well above sea level. But what's going to happen is as the water begins to come in, we're going to see water moving in through here, through this plain, through this region, this plain here. So water's going to come down here. It's going to come in from the Gulf as well. So here we go. So in the early Cretaceous, the sea level goes up. We see water coming in from the Arctic, working its way down the eastern side of the Rockies. So the Rockies are still above sea level, but the rise in sea level is sufficient to overcome the increase in the western side of North America caused by the formation of the Rockies. So we can see the water begins to come down along the eastern side of the Rockies. It also begins to move northwards from the Gulf region. We can also see that, well, we can see by the Middle Cretaceous there's a slight retreat going on. As we move into the Late Cretaceous, there's a real burst of activity. And at this point, we can see we now have a body of water that goes all the way from the Arctic, all the way down to the Gulf of Mexico. We also have the formation of another branch over here that goes from essentially Alberta and Saskatchewan over here. Sorry, what I'm saying, Alberta and Manitoba, and goes all the way through to essentially the coast, around Newfoundland, Greenland, that kind of area. Essentially along what is now the modern day St. Lawrence, give or take a little bit. And then you can see as we move from the Late Cretaceous into essentially the Cretaceous tertiary boundary, we can see that the Zuni Empiric Sea is in full retreat. So it's retreating out towards the North Atlantic, out towards the Arctic, and back towards the Gulf of Mexico. So that's the Zuni Empiric Sea. You can see that essentially even at its maximum extent, there were still large quantities of continental North America exposed above sea level, and that means these seas would have been absolutely stuffed with clastic sediment being formed from the erosion of these areas of continental crust. So, good. This is actually quite a good time to pause for a second. So, pause the presentation. Get up, have a walk around, get a glass of water, and please come back in a couple of minutes. So, as we've been going through the Paleozoic into the Mesozoic, one of the things that's been near consistent is the fact that when it comes down to it, we've only really had, 2 or 3 major land masses, and so this has meant that the oceans could circulate rather freely. Now, when an ocean can circulate rather freely, that means warm water from the equator can move northwards or southwards towards the poles relatively easily and relatively quickly. And so this means that warm water helps to keep these higher latitude regions artificially warm. So a classic example of that now is the United Kingdom. So the United Kingdom is kept warm by the Gulf Stream, and that's essentially a river of water that goes from the Caribbean Sea and it goes all the way across the North Atlantic, and it makes, it hits essentially the area around the United Kingdom and Ireland, and it helps to keep the water around the United Kingdom artificially warm. So one of the things you probably know about the United Kingdom is that it's an extraordinarily wet country. It has heavy rain at least 100 days out in the year. The rest of the time it's normally great. I should know, I live there. Now, one of the things that people don't realise about the United Kingdom, though, is that it's actually on the same latitude as Moscow. However, the United Kingdom is not known for its particularly cold winters. Moscow, on the other hand, if you've ever been there in the winter, you will know it has very significant snowfall, and temperatures can get down into the -30 kind of range. So what's making the difference? Well, the answer is the Gulf Stream. That river of warm water coming across the North Atlantic helps to keep the United Kingdom artificially warm, and so it means that the winters are nowhere near as harsh as they could be. So it helps to keep the climate more stable, and that's exactly what was going on all the way through the Paleozoic. You had all this warm water coming from the equator, going towards the higher latitudes, helping to keep the temperature up in those areas nice and stable. Now, what's going to happen as we move through the Mesozoic is, as you've seen, all the continents begin to break off from one another, and we end up with all the modern continents all moving towards their current positions. Now, this is obviously going to affect how the water in the ocean circulates. And how the water in the ocean circulates is going to have a direct effect on how the air in the atmosphere moves. That's going to affect wind directions. That's then going to affect essentially the global distribution of certain, climatic bands. So the general trends that we see is we tend to get areas with dry climates that will occur on large land masses and areas that are remote to sources of moisture. So the further you are from a sea or an ocean, typically the drier your climate will be. And once again, the classic example of that is Asia. So if you look, if you ever look at a Google Earth image of Asia, what you'll notice is the center of Asia, the kind of Mongolia, Western China, Tibetan Plateau into Kazakhstan, Tajikistan, areas like that. That area is on the whole either desert or semi-desert because it has a relatively low yearly rainfall. On the other hand, areas that tend to have relatively high rainfalls will often be situated near large bodies of water, typically towards the coast. And so once again, if you ever look at a Google Earth image and you just zoom out of the Earth, what you'll note, zoom out and look at the Earth as a whole, what you'll notice is that the vast majority of the greenest areas are located, shock horror, near the coast. So we know that these general trends exist, so that we can make very broad predictions based on those two trends relatively easily. So we know, for instance, that through the Mesozoic, the land mass that is Asia. So if we just zoom back here, go back a few slides for this one. So we know that during the Mesozoic, we know that this large landmass here, which is modern day Asia, we know the core of it's going to be quite dry, and so we can say, right, we'll have arid or semi-arid conditions here. Whereas we know that these areas around here that are close to the coast, well, we can say with relative certainty that these areas are on the whole going to be quite wet and therefore, quite heavily vegetated. So, we can make those broad assumptions straight away. So what else is going to give us hints about the past climate? Well, as we've discussed in the past, there are certain sediments and certain things that we see in sediments that allow us to infer environments. So these are sediments that are essentially sensitive to climatic effects. So one of the classic examples of that is evaporites. So if you want to form layers of evaporites, obviously you need an arid to semi-arid climate. Okay, so whenever we find layers of evaporites in Mesozoic rocks, well, clearly we know that during that time period, that area must have been relatively dry. Same goes for red beds. So when we find sandstones that have that distinct rusty red colour to them, well, once again, we know that essentially those rocks must have formed, or should I say, are very likely to have formed in a hot, arid or semi-arid climate. And then we have rocks like coal. Obviously, coal likes to form in warm, humid, swampy environments. So once again, when we find layers of coal in Mesozoic rocks, we can say that during the Mesozoic, that area was essentially warm and swampy. And there's actually one that I missed off the list there. The other one is, of course, limestones. Limestones like to form in warm, shallow seas. And so, once again, if you find limestones, chances are you were dealing with an area of the sea that was warm and shallow. Okay, So the Triassic sees the deposition of extensive red beds with cross beds in them, so we know there are dunes. There are lots of evaporites around, and so that clearly indicates that there were dry conditions in North America, South America, Europe, and Africa. And that makes perfect sense, because at this point in time, Pangaea is nearly still complete, so we have one huge landmass. So if we go all the way back, sorry about this, so if we go all the way back to the early Triassic, you can see that these huge landmasses, these areas that are well away from the oceans, are going to be very, very hot, very, very dry, and so we're going to have huge areas of desert in these regions here especially. Oh, got to keep going. There we go. Okay, so in contrast, Triassic sequences from higher latitude areas, so that's more towards the poles, tend to contain coal beds. So that would indicate that as we moved towards the poles during the Triassic, temperatures dropped a little bit, or at least the amount of humidity increased, and so we ended up with environments where having temperate, swampy environments in which we could form large quantities of organic material became possible, and then therefore we had coal swamps. So conditions would have been equivalent probably to modern day peat bogs, or in some cases tropical wetlands. So depending on exactly how hot the climate was, you would have formed build-up of organic material that would have either been like peat, which is the kind of thing you could expect in places like Ireland and Scandinavia, so much lower temperatures, or in areas that would have been warmer, you would have expected more tropical wetlands to form, kind of equivalent to the Florida Everglades, for instance. So in some cases, we can make relatively strong inferences about the type of environment an area was under during the Mesozoic. However, there are some areas where we just don't have that evidence, and so the rocks there are maybe pretty generic, and so we can't really draw many conclusions from them. And so what we have to do is we have to start inferring the probable climate based on some logical hypotheses and evidence from other proximal locations where we do have evidence about the climate. So a good example is that rocks throughout the Mesozoic show the equatorial regions were warmer, and we have evidence to prove this. So, sorry, I'm going to start that sentence again because I completely lost my train of thought. I do apologise. So, yeah, rocks throughout the Mesozoic show the equatorial regions were warmer, and we have evidence to prove this. So we have lots of desert sediment. So we know that the equatorial regions during the Mesozoic were on the whole quite dry. We also know that the northern and eastern margins of the Tethys Ocean were broad, shallow, warm seas, and we have the carbonate deposits to prove that. So we can model how water would have circulated around the Tethys Ocean and how it will affect weather patterns. So once again, if I just go all the way back up here, well, we know that the northern portions of the Tethys Ocean and the eastern portions here, well, they were limestone producing factories. So we know that these areas here would be marine, warm, shallow water, and we know that during the Mesozoic the entire equatorial region was nice and warm, just like it is now. So we can make inferences about how the water would have been circulating around in the Tethys Ocean. Now, once we know how the water's moving around the Tethys Ocean, that then means we can make predictions about how the air was moving in the atmosphere, and so that's going to allow us to essentially work out what the likely weather patterns would have been, in this area of the Tethys Ocean during the Mesozoic. So even if we don't have evidence for, let's say what the climate was like here, based on our modelling, we can make a very educated guess. So if we continue our example, so even though we have little direct evidence to prove it, we can say that the northern and eastern boundaries of the Tethys Ocean were hot and humid. So we don't really have the rocks to show what the conditions were like there, but we know that the continental rocks in that area were probably hot and humid. And based on our modelling of the weather patterns, we can say that there would have been moist winds coming off the Tethys Ocean, and that would have caused seasonal monsoons. So conditions would have been a lot like modern day Southeast Asia now. So next question is, when it comes to discussing past climates, can we come up with solid numbers? The answer is no, we can't. So the temperature gradient between the tropics and the poles affects oceanic and atmospheric circulation. So the greater the difference between the poles and the equator, the higher the temperature gradient and the higher the rate of circulation. So if the poles are very, very cold and the equator is very, very warm, the water that's circulating between the two will go very, very quickly. What we also know is we know that the oceans will absorb more solar energy than the continents. So seawater will absorb about 90% of the solar energy that hits it, whilst the continental crust will only absorb somewhere in the region of 50. So essentially the seas are much more efficient at absorbing sunlight. So that means we can say areas that are dominated by the oceans are clearly going to be warmer than those that are dominated by continental crust. So by knowing the position of the continents at a given time, we can model ocean and atmospheric circulation and the effect of heat retention by the oceans and the land masses, so we can produce estimates of annual temperature for regions on the Earth's surface. So, just through some relatively basic assumptions, based on, what we know from the modern environment, we can come up with broad assessments of what annual temperature would have been like, on certain parts of the Earth during, the Mesozoic. So what we notice is the breakup of Pangaea in the late Triassic caused the global temperature gradient to increase significantly. So why is this? Well, during the late Triassic, we begin to see the northern hemisphere continents move north. So North America, Europe and Asia start moving towards the North Pole. Now, as they start moving towards the North Pole, what that does is it displaces seawater. Remember, seawater is really, really good at retaining heat. Continental crust is nowhere near as good. So as North America, Europe and Asia move northwards, well, the northern hemisphere, or at least the higher latitude portion of the northern hemisphere, starts getting colder because there's less seawater up there to retain heat. And so we begin to see a shift in the sediments in North America, Europe and Asia. Throughout the Cretaceous especially, we begin to see this shift from relatively warm weather sediments into colder, more temperate weather sediments. We can also begin to see that there may be some seasonal variation beginning to appear as well. Start getting cold winters and warm summers. So when changes in ocean circulation occur, it also has an effect on the atmosphere. So as Pangaea breaks up, it's also going to change how the atmosphere circulates and therefore how the winds in the atmosphere move. So when we combine this data on how the air in the atmosphere starts moving, or at least changes how it moves, and the combination of this more rapid ocean circulation, we begin to be able to come up with, a relatively good model of how the climate began to change through the Mesozoic. And so what we see is, especially in the Cretaceous, as the continents begin to separate from one another fully, we begin to see that ocean circulation becomes far more chaotic. We begin to see that, well, we can see it here. So here's Pangaea. We can see the ocean is circulating freely. Therefore, we have good homogenization between the equator and higher latitudes. As we move into the Cretaceous, we see North America and Europe and Asia pushing north, replacing warm seawater up here with cold continental crust. So the northern hemisphere starts to get colder. We can see that Antarctica starts to move fully over the South Pole, so we're going to get large-scale glaciation forming there, which is going to help to cool down at least the area around the South Pole. And we can also see that this nice open circulation of seawater begins to get completely destroyed as all the continents start to move in their own directions. We start to get very localized circulations of water. And this is all going to affect how the seas circulate and also how the atmosphere circulates. And so what we know is as we move into the Mesozoic, especially the Cretaceous, we begin to see a significant change in global temperature. So we begin to see the poles get colder. We also begin to see the temperate band begins to move south. That means the equator starts to get squished, so the equatorial region starts to get a little bit compressed. And we begin to see far more chaotic weather. And by chaotic weather, what we really mean is seasons. So we begin to see evidence that in the northern hemisphere, we start having a winter, we start having a summer. Same goes for the southern hemisphere continents. So all of a sudden, if you're a reptile like a dinosaur, and you really, really love it when you have constant hot conditions, well, all of a sudden, if you're living in North America and from November all the way through to March, all of a sudden the temperatures are getting pretty darn low, well, you're going to be in a lot of trouble. And so this breakup of Pangaea is one of the reasons that the population of dinosaurs starts to become stressed. Because all of a sudden you have dinosaurs that like living in these, relatively warm, relatively dry conditions, and all of a sudden they're finding that their climate is becoming, colder, especially for part of the year, and maybe in some areas it's typically becoming a lot wetter and a lot cloudier, so that means less sunshine. So that's obviously going to start stressing the dinosaur population quite severely. It also means that air circulation is going to move more towards the modern pattern. So if we look at this diagram down here, it shows you how air moves in the modern environment. So let's have a look at the globe. So what you'll notice is, here's the equator, this dark blue line here. You'll notice that air moves towards the equator, and you'll also notice that air moves away from this pink line towards this low pressure line here at about 60 degrees north. Okay? So what this means is air gets pulled away from this band here about 30 degrees north and south of the equator. So what this means is all the air gets pulled away from here, so we're left with a band essentially of relatively dry air in this area. And you'll notice that when we look at where the deserts are located, there's the 30-degree band there, north, and here's the southerly 30-degree band here. So what this eventually ends up causing is it ends up causing essentially the atmosphere to begin to separate into these distinct bands, and we end up setting up the kind of climatic zones that we have now. Okay, so we've been going for an hour again, so this would be a good time for a break. But before you go, let's do today's code word. So today's code word is Beowulf. Yeah, do you know what that is? I'm sure some of you might not. So Beowulf is a famous Anglo-Saxon, so Old English story. You can guess I'm kind of running out of things to do code words about. I'm staring at my bookshelf right now, and it was the first book that I saw. So that's Beowulf. That's Beowulf. So make sure you write that down for the code word quiz. Okay, so pause the presentation, get up, have a walk around, go in a glass of water, and please come back in a few minutes. Okay, so what's happening in the Mesozoic for North America? Well, conditions in the early Mesozoic were a continuation of those experienced in the Permian. It was very hot, and it was very arid over a large quantity of North America. So essentially conditions in the Triassic were very similar to those of the Permian. So terrestrial sedimentation persisted, although we had rifting and volcanism increasing as North America began to separate from Africa along what is now the modern Appalachian Mobile Belt. So we had a shallow sea created in the Gulf of Mexico, and that for a period of time became a restricted basin. And due to the fact it was in an arid climate, you had substantial quantities of evaporation, leading to sequences of very, very thick evaporites being deposited in the late Triassic and very early Jurassic. And then we get the global sea level change during the Cretaceous, leading to the formation of the Cretaceous interior seaway and the deposition of a new sedimentary sequence. So if you remember, that's the Zuni sequence. So on the west coast, we have a Permian volcanic island arc system suturing itself to North America during the late Permian and early Jurassic, and that leads to the Sonoma orogeny. We also have the Cordilleran region undergoing a series of orogenies, producing the Sierra Nevada, the Rocky Mountains, and a few other lesser mountain chains. These are all lumped together generally and referred to as the Rockies. So these orogenic vents are bundled together as the Cordilleran orogeny. Okay, so what's happening in the center of North America during this period? So during the Paleozoic, there were 4 marine transgressions and regressions: the Soak, the Tippecanoe, the Kaskaskia, and the Absaroka. If you remember, the Absaroka straddles the boundary between the Permian and the Triassic. So the resulting empiric seas were the focus of the deposition of lots of sediment, and we have unconformities at the top and bottom of these sedimentary sequences. So these sedimentary sequences are far less important in the Mesozoic, where the continent's interior remained above sea level for the vast majority of the Mesozoic. So the 2 Mesozoic cratonic sedimentary sequences are, of course, the Absaroka, which is Middle Carboniferous to Early Jurassic, and the Zuni, which is Early Jurassic to very, very early Paleocene, so just into the Cenozoic. So neither of these transgressions managed to inundate the continent to the same degree experienced during the Paleozoic. So on the whole, these sequences were nowhere near as expansive. Alright, so what's going on the East Coast during the Mesozoic? So during the earlier Middle Triassic, we have coarse detrital sediments produced by the erosion of the Appalachian Mobile Belt, and they were spread by rivers and wind over the surrounding area. So we have the erosion of the Appalachian Mobile Belt here, and we have rivers depositing those sediments to the northwest and to the southeast. We have the continued erosion of the Appalachian Mobile Belt throughout the Mesozoic, and that's going to reduce this once Himalayan-sized mountain range to essentially a set of gently undulating hills. And there is some argument to suggest that by the end of the Cretaceous, the Appalachian Mobile Belt was completely flat and was in fact a river plain. So, topography-wise, it would have looked quite a lot like the area around Houston. So in the late Triassic, there was crustal extension due to mantle upwelling under Pangaea, and that caused a rift to develop that extended from Nova Scotia down the east coast of the United States, terminating somewhere around North Carolina. That's essentially where it started. And so we can see it here on this map here, these areas marked out in this kind of brown color, these represent areas of rift-related volcanics and sediments. So this entire area was undergoing extension, it was being stretched. And as I already touched on, when you start stretching a rock, initially for a short period of time, it will behave like a liquid, it will behave like a piece of silly putty. As you stretch it, it will begin to become thinner. Now it will only do that for a little while. Eventually you get to the point where the rock won't stretch anymore, at which point it will just simply break like a solid. So if we look at this diagram here, we can see this is the kind of situation we have in these regions here. These rocks have undergone extension, and as they've been extended, they've broken into these big fault-bound blocks. So they've got a fault on one side and a fault on the other. And so as the crust was stretched further and further and further, one block would drop down, another block would drop down, drop down, drop down. So the blocks would drop down relative to each other. And this produces a depression, otherwise known as a rift valley. So these are big normal faults, okay? And we can see, so if we look at this picture here, this is actually a rift valley here. So we can see this is one fault block up here. So this flat surface, this flat cliff face here, that's the fault. Okay, so let's say this represents this fault block here. Okay, so then we have this fault block here. Okay, that's dropped down relative to this block up here. And so let's say that's this block here. Then we actually have this fault block here, which is the one the photographer's standing on. Okay, this has dropped down relative to this fault block here. So let's say that is this fault block here. So what we have essentially is we have blocks of rock dropping down relative to each other as the crust gets stretched. And you can see it's formed a topography. The person taking the photograph is much, much lower than the initial land surface up here. And so as this entire area undergoes extension, you end up forming a long linear rift valley. Now obviously what happens is these faults here become a channel for magma. So as this crust gets thinned, the mantle underneath is under lower pressure, and of course it starts melting. And as we've already discussed, that melting magma is going to produce a mafic magma that's going to enter the crust, and it's going to work its way through the crust, and it's going to focus itself primarily along these faults here. They're going to be nice, easy pathways along which the magma can move. The other thing that's going to happen is these highland areas that are produced by the faulting, these areas up here, well, these are going to erode. So this area here is going to erode faster than this area down here. And so the highland areas produced by the rifting are going to be eroded. They're going to produce clastic sediments that are going to be deposited into the rift valley. So the rift valley is going to be a mixture of clastic sediments produced by erosion and typically mafic volcanic rocks, a lot of mafic dikes, and a lot of mafic silts. So the erosion of these highlands produced essentially a sequence of sediments which is referred to as the Newark group, and it's dominated by red terrestrial sediments. That tells us the sediments are being eroded and deposited into a rift basin in an arid or semi-arid environment. So the deposition of much of the Newark group started in the late Triassic, and so that gives us an idea. About when, I do apologise for that, that was one of my children. So the deposition of the Newark group started in the late Triassic, although some areas didn't start until the early Jurassic. So if you remember, the rifting started in the northeast and worked its way down towards the southwest. So we see the rifting started first in the northeast, so we get the oldest parts of the Newark group in the northeast, and as the rifting progresses southwest, we get steadily younger and younger sedimentary rocks being formed. So as well as the detrital sediments from the erosion, we obviously get the formation of extensive lava flows, and obviously these lava flows have to be fed by an underlying pipework, and so within the Newark group we have lots and lots of dikes and sills being intruded. All of it's mafics, mostly dominated by basalt. So as the rift widened, eventually the margins became passive and we formed a proper ocean basin. So when we form the North Atlantic proper and we start forming oceanic crust at a spreading ridge, well, at that point the eastern seaboard becomes a boring, passive margin. Nothing much happens. It becomes nice and dull. So by the early Cretaceous, any remaining Appalachian highlands are gone. The area is almost flat. And so essentially, nothing's going to happen until the Appalachian region is once again lifted up. And that's going to occur during the Cretaceous. So during the early Cretaceous, the entire thing's been plain flat. Then there's a short period of uplift. That pushes the area up for a little while. There's a round of erosion, that's going to deposit around 3,000 meters of sediments onto the passive margin, and then the uplift's going to stop again, and the entire area is going to become a flat river plain once again. So, just to give you some idea of the Newark group sediments, so here we go. You can actually see the Newark group sediments, these nice red, mostly sandstones. You can see them there. The red colour obviously tells us they're being deposited into an arid to semi-arid environment. And you can actually see we have this big layer of rock here. This is a sill. So this is a layer of mafic magma that's been injected parallel to the bedding. And so that gives you some idea of the quantity of magma that was moving underground. So large quantities of magma, being intruded into the crust during this period of extension. Okay, so what's happening in the Gulf region? So in the Gulf region, the area was once again above sea level for much of the Triassic, as it was a highland area created by the Achetan orogeny. So the rifting that began along the east coast during the Triassic took a little longer to reach the Gulf area, and rifting probably started somewhere around the early Jurassic. So once rifting began, we form a rift valley, so we form a topographic low, and that topographic low eventually becomes deep enough to fill with water from the Pacific Ocean, and that produced a shallow restricted basin. And that restricted basin obviously underwent evaporation, and that led to the deposition of quite a thick sequence of evaporites, approximately 1 kilometer's worth of them. And that occurred, as I say, typically during the early to middle Jurassic. Now, by the late Jurassic, the rift had opened up even further. This meant even more water could flood in from the Pacific, and so that stopped the evaporation. So essentially, that's the point where the evaporite deposition stops. So during the Jurassic, the Gulf became a passive margin, and sediments were eroded from what was left of the Achetan highlands to the north, and they were deposited onto the newly formed continental shelf. So the Jurassic sequence displays several cycles of facies changes caused by minor marine transgressions and regression. So essentially the south coast of North America is exposed to lots and lots of sea level changes, going up and down quite a bit. So by the early Cretaceous, the Gulf region, like much of the western margin, was flooded by the northward was flooded as part of the Zuni sequence. And as you know, eventually the body of water linked up with the body of water coming from the Arctic Sea, and that created essentially the Cretaceous interior seaway that stretched from the Arctic all the way down to the Gulf of Mexico. So that pretty much covers what's going on for the Gulf region. So by the time we make it into the very late Jurassic and into the Cretaceous, you can see we have this body of water that extends from the newly forming Gulf of Mexico all the way up to the Arctic Ocean up here. So during the Cretaceous, the Gulf region was an excellent environment for reef building. So this area down here was a prime location for large-scale carbonate formation, and that's exactly what happened. And so the area became covered in reefs. And so the Cretaceous reefs were dominated by an organism which is referred to as a rudist. It's a type of bivalve, and it has this distinct horn shape to it. So the lower valve has this kind of, cone shape, and the upper valve forms a lid. So due to their large size, these rudists essentially would form huge reefs, and obviously when one rudist fell over, a new rudist would just grow on the shell of the old rudist, and so eventually the limestone that's formed by these rudists is essentially just a pile of rudists. So it's very, very porous. There's lots of gaps in between them. And so that makes this particular limestone that was forming during the Cretaceous an absolutely excellent reservoir rock for oil, because there's lots of porosity for the oil to move into. So you can kind of see, so here's a nicely preserved rudist here. Here's a hand specimen that shows you a number of rudists altogether. And this picture behind, just going to go back there. And this picture behind shows you two rudists. So this rudist here, you can see, you can kind of make out the core of it there. And you can see the shell coming around here like this. And it's missing its lid. Now this rudist over here is the same thing. So here's the cone. That's one half of the valve. Here's the edge of the cone coming around here, and you can see this kind of honeycomb looking material. That's the lid. Okay, so you can see this valve, this particular rudist is actually, more or less complete. So the position, the situation in the Cretaceous will look something like this for the Gulf Coast region. So we would have had closest, so we would have had North America up here, deeper water down here. And obviously we would have had several rudist-dominated reefs forming that would have protected a carbonate lagoon behind. And so within that lagoon, obviously we would have had a build-up of essentially carbonate muds. And obviously we would have had lots and lots of life in this area as well. So this carbonate lagoons would essentially be dominated by, macritic carbonates, lots and lots of shells, lots and lots of fossils, ooids and other, carbonate particles would also have been present. And so you can essentially see it's the classic carbonate platform, really. In terms of the western region, what's going on there? So with the exception of the East Coast Rift Zone that began in the late Triassic, everything that's going to happen in terms of tectonism during the Mesozoic is focused on the West Coast. It's the West Coast where it's all happening. So the West Coast was also the site of two major seaways, of course. We have during the Jurassic, we have the Sundance Sea. And during the Cretaceous, of course, we have the Cretaceous Interior Seaway. Both of those bodies of water are, of course, part of the larger Zuni transgression. Now, in terms of the western region, as you can see, because it's an area that's undergoing active tectonic deformation, of course, the area is an upland area, mountainous area throughout the entire Mesozoic. And so, on the whole, it never really drops below sea level, and of course the area is undergoing lots and lots of active erosion, leading to the formation of large quantities of detrital sediment which are going to be deposited into the Cretaceous Interior Seaway. Obviously, sediments are also going to be deposited to the western side of the Cordilleran Mobile Belt. However, of course, remember this sediment is coming off the belt onto this side here, and of course this is an active continental margin. So this area here is undergoing extremely strong deformation due to subduction. So we don't get nice sedimentary layering in this area. It's all a bit of a mess. Alright everybody, so that's it for this presentation. So please remember the code word for this presentation was Beowulf. That's Beowulf. So thank you for sticking with me through this presentation. I know it wasn't a particularly great one. I apologise for my son interrupting. Remember the code word, make sure you write it down for the code word quiz, and keep an eye out for the next presentation.